Hello. In this video, we're going to take a look at the definition of logarithm and also take a look at the graphs and in particular asymptotes for logarithmic functions. If you know logarithms very well already, this will be a review video, but if you're still a little shaky on what is a logarithm, this one might be worth looking at. For example, let's start with the function f of x equals 5 to the x, a typical exponential function. The graph is shown below. Because 5 to the x makes sense for any real exponent x, this function has domain or a set of inputs, a set of all real numbers. On the other hand, 5 to the x is also always a positive number. It can never be negative, and it can never be 0. And so the range or set of outputs is the set of all positive real numbers. So we see none of the graph down here. And by the way, there is a horizontal asymptote to the exponential function here along the negative x-axis. And we can see this graph passes the horizontal line test. Every horizontal line we draw hits the graph in at most one point. And of course, that means that this function has an inverse. The inverse function is denoted f inverse of x, and as we saw in the last video, the graph of the inverse can be found by reflecting the original function in the line y equals x. We've done that over here. Here's the line y equals x. And the blue exponential graph is reflected into the orange inverse graph. Now let's explore this inverse function. Let's start by considering the equation 5 to the a, or f of a, equals 12. We want to know what number a should we raise 5 to get the answer 12. That's illustrated out here on the graph, where we see we'd like an input a up to the graph that gives an output of 12. We could also think about working that example backwards too, start from 12 and then trace backwards to get a. We can also express the solution to this equation using the inverse function. We can write a equals f inverse of 12. The inverse function takes the output 12 and gives us the input a back. And if we take a look at the graph, the situation might look like this. So down here, again, the orange function is the graph of the inverse. We can see taking this number 12 and taking that as input to the inverse function, and then out of that comes a. Remember, since a is the inverse of x, a is the input we need in the exponential function down here to give us the answer 12 back. But does that give us much insight into f inverse of 12? Because a denotes the number for which 5 to the a equals 12, we could write this relationship in a number of ways. For example, we can write 5 to the f inverse of 12 equals 12. Again, because f inverse of 12 is the input for which the exponential 5 to the x gives output 12. There's really no easy way to express the value of f inverse of 12. So we make up a notation for this. This is a very important number, very important notation. Instead of writing f inverse of 12, we denote that by logarithm to the base 5 of 12. So this is the logarithm notation. Logarithms are defined just to express solutions to exponential functions or equations like 5 to the a equals 12. So from now on, we'll write 5 to the a equals 12 has solution a equals log base 5 of 12. The little number down here, as you know, is called the base of the logarithm, the 5. And that means there is a 5 to the x exponential function lurking in the background. And of course, 12 is the output we want from the exponential function. And so we can think of the logarithm again. Log base 5 of 12 is the number to which we will raise 5 to get the answer 12 back. Again, we don't know what it is. We don't have a good way to solve for that in terms of, say, radicals or trig functions. So we make up this new notation, this logarithm notation. Other ways to express this relation are the following then. So we can write 5 to the power, log base 5 of 12 is 12. Again, because log base 5 of 12 is the number we raise 5 to get 12 back. And likewise, if we reverse the composition, if we take the log base 5 of 5 to the a, this is saying what number must I raise 5 to get 5 to the a back? Well, duh, the answer is a, of course. In general, if b is positive and not 1, then the function fx equals b to the x has an inverse, and this inverse is denoted by capital F inverse of x is log base b of x. The function y equals f of x equals b to the x, as before, has domain, all real numbers are, and the range, the y outputs you can get are y bigger than 0. And of course, the way the domain and range of the function interact with the domain and range of the inverse, that means that f inverse log b of x, it takes as input the outputs of the exponential function, so it has domain x is bigger than 0, and the possible outputs are the domain of the exponential function, and so the range of the inverse function is all real numbers. And the two fundamental relationships linking these, we saw these in the last slide with 5 instead of b, are b to the log base b of x equals x. This is because log base b of x is the power you have to raise b to get x back. And x is only positive because we can only get positive answers out of the exponential. Likewise, log base b of b to the x equals x. To what power do you have to raise b to get b to the x back? Well, to the x power. You really want to know these. These combinations will come up a lot in our work, and remembering these relations will help in doing simplifications later on. Now the case b greater than 1, I'm going to look at this case and the case b 0 less than b less than 1 in just a moment. But the case when b is bigger than 1 is typified by our previous example, f of x equals 5 to the x, in which case the f inverse function was log base 5 of x. And as we saw earlier in the video, we have graphs looking like this. Okay. Now I want to point out a few things about this graph. Notice that the graph of 5 to the x, as I said earlier, has a horizontal asymptote along the x-axis, that is in the minus infinity direction. And when we do the reflection about the line y equals x, this horizontal asymptote becomes a vertical asymptote down here. And so it's a vertical asymptote for the graph of y equals log base 5 of x. Now we can see here that as the inputs, over here, as the inputs to the logarithm function go towards 0, that is get closer to 0, we see the outputs come out down here, they get large and negative. And so this negative y-axis asymptote is described, or the analytical description is given by the limit as x goes to 0, log base b of x equals plus infinity. And this should be x goes to 0 from the positive side, because we can't come in from the negative side because there's no graph. So that was a typo in the slide. That should be x goes to 0 from the positive side. So again, this is an important relationship to keep in mind about the logarithm. Logs of small numbers, when x is small and positive, turn out to be large and negative, as that typifies. We're going to encounter these b greater than 1 cases for the log and exponential later on. This case arises in the study of population dynamics, compound interest, the spread of disease or rumors, and other similar phenomena. Now, if b is between 0 and 1, let's take as an example, capital F of x equals the number 1/2 raised to the x power, and then the inverse function, f inverse of x, will be the logarithm to the base 1/2 of x. Now, you might pause the video a moment and try graphing these two functions to see what they look like. but here we see it. As you raise 1/2 to a large power, you're going to get small numbers. And so that's why this thing dies off as x gets large. In fact, we have an asymptote here in the positive infinity direction. So this exponential is a decreasing function. And when we do the reflection about the line y equals x, we get the orange graph, which is the inverse function, or log base 1/2 of x. Okay. So again, keep in mind when b is between 0 and 1, the exponential function falls, as we see in the picture. That is, the function is decreasing. We see there. And the reflected graph, y equals log 1/2 of x in orange, also falls as x gets larger. So the logarithm graph is also decreasing. Again, it's only defined for x is bigger than 0. Again, that's for this logarithm graph. And again, we note that what happens to asymptotes? The asymptote in the positive infinity direction here reflects into a vertical asymptote for the logarithm function. Now the logarithm heads off to plus infinity as x approaches 0 from the positive side. And so this vertical asymptote for the log function is described analytically in that way. As x gets small and positive, the log to the base 1/2 of x is plus infinity. Well, it gets large and positive, and so that limit is plus infinity. Now, there are times we'll want to work with exponentials of numbers between 0 and 1. That does happen. And this arises in the cases of radioactive decay, environmental restoration, Newton's law of cooling, and other similar physical phenomena.